that to obtain the inverse of a function, f, from its graph, we reflect that curve through the line y equals x. Again, the way to obtain the inverse of a function, we said, if we have y equals f of x, is to switch x and y. For example, here's another example. If y equals x squared, we can switch x and y, and that gives us x equals y squared. So I don't mean like put y over here and x over here, so you get y equals x squared. That doesn't do anything. I'm saying switch the variables. So wherever you see a y, you replace it by x. Wherever you see an x, you replace it by y. So then we get this. X equals y squared. Now, it's very important to realize that this is not an algebraic operation. In other words, we often say that you can add 2 to both sides of an equation. And this has nothing to do with that kind of thing. When you add 2 to both sides of an equation, you don't change the equation. However, here, you get a completely different picture, right? You get a completely different function. In fact, we call it the inverse of the original function. So it's not preserving the same function. It completely changes it. It's just a trick to find the inverse. Okay, so what's the trick? You switch x and y. So we do that. Then we solve for y. Then solving for y, we get y equals x squared. So we have this, we solve for y, we get y equals x squared, which is the inverse. Also note that if f inverse is the inverse of f, is the inverse of f, then f of f inverse is equal to x, and f inverse of f is also equal to x. Okay, now let's review the function y equals e to the x. So we know that y equals e to the x looks like this. We can graph a few points. We can put in x equals 0. We can put in x equals 1. We can put in x equals 2. We can put in x equals negative 1. When we put in x equals 0, we get e to the 0, which is 1. When we put in x equals 1, we get e to the 1, which is e. When we put in x equals 2, we get e squared, which is something. It's like 2 squared or 3 squared, somewhere between there. We put in negative 1, we get 1 over e. Okay, so now we want to talk about the function y equals log base b of x. For example, y equals log base 10 of x, or y equals log base 2 of x. This is called the log base b of x. So what does it mean, and how is it defined? For example, suppose that b is equal to 10. Just take an example. So we're talking about this function. And so if we ask, for example, what is the log base 10 of 100? So how do we do that? So maybe you remember how to do this. Maybe you remember what the answer is. The question mark is defined to be the number, that is, this is defined to be the number that you have to raise 10 to get 100. So what do you have to raise 10 to get 100? So it's pretty clear that you have to raise 10 to the second power to get to 100. So in other words, it's this. This question is this. So it's what do you have to raise 10 to get to 100? And this, the answer to the log base 10 of 100 is whatever that is. So in this case, this is 2. This is going to be 2. Okay, so because of this, what do you have to raise 10 to get 100? And the answer is 2. Note that this is actually an exponential question, right? So this is actually this question, and that's actually an exponential question, right? So the log base 10 of 100 is actually some kind of exponential question. It's this question here. The log base 10 of 100 equals what is 10 to the what equals 100? Of course, the answer is question mark equals 2. So question mark equals 2. So this equals 2. Or another example, suppose we said log base 10 of 1,000. So what's the corresponding exponential question? It's 10 to the what gives you 1,000. And the answer, 10 to the what gives you 1,000, is 3. So question mark is 3. So this is 3. So more generally, what does this mean? This means b to the what equals x. That's what this means. B to the what equals x. So the log base b of x is asking the question b to the what, b to the y, which y, equals x. Okay, so we have this. Now let's think about what we were doing before. Let's think about what's the inverse of this. So how do we do the inverse of this? So we know that to do the inverse of this, we just switch x and y. So if we do that here, if we switch x and y, what are we going to have? We're going to b to the x equals y. So we get b to the x equals y. So that's the inverse of this. So that's also the inverse of this, because this is this. These are the same question. Okay? So the inverse of this is this. And this shows that the relationship represented by b to the x equals y, that is this, is the inverse of the relationship represented by this, but this is the log relationship. This is just another way of writing the log relationship. So what we see is that that is the relationship between x and y represented by this, is the inverse of the log relationship. So the log is some relationship between x and y, and what relationship is it? We can say that it's the inverse of this relationship. But this relationship, we know something about it already. We know what it looks like. We've graphed it. Thus, the log base b x equals y is the inverse of this relationship. This tells us what to expect for the graph of this. It's going to be the inverse of the graph of this. Okay, but we know the graph of this looks like that. And if we draw this line, then we know the graph of y equals log base b of x is going to look something like this. It's going to be the reflection of this through here. Now this, I think we've said that exponential functions grow very, very quickly. So this is conversely is going to grow extremely slowly. So whereas like this function, the orange function, grows we can sort of say more quickly than any possible polynomial function. Doesn't matter what you raise, what power you raise the polynomial to. Like you could raise a polynomial to the 100th power or the 1000th power. This is still eventually going to grow much, much more quickly than that. But this is going to grow much, much more slowly than any lower degree polynomial. This is going to grow very slowly. Okay, so now let's talk more about this function. So y equals log base b of x. So we have a special name when the base is in particular e. Like we can have any kind of base here. We can have e, we can have 10. Well, we can't have any base. We can't have negative bases, and we can't have 0 base. But any other bases we can have. So we could have 10, we could have 2, but we could also have e, log base e. So, but that has a special name. And instead of writing it like this, you can write it like this.